Alright everyone, this is a video on what is representation theory. So what is representation theory? Well, it's this really difficult to explain concept, and it has a lot to do with algebras and Lie algebras, but another group is presenting on that, so we will be presenting representation theory as it pertains to using matrices and other forms of representing groups and sub-representations of these groups. Let's start somewhere. So, what is representation theory? Basically, it's the ways we can represent group actions and group symmetries. Okay. So, a group symmetry on like S3 or on D3 basically has the form of this when you take it into like a Cayley diagram. This would be a form of representation, but this isn't really our main goal. Here's another Cayley diagram. You can see that there is different ways of representing things. That is the kind of concept we're going to try to get at. So, we want to think about how a vector space can be naturally represented by the matrices that show linear transformations on those vector spaces. So, this will be called the standard representation of GLV. Okay, this is going to be a lot of notation-heavy stuff, but I believe in you guys to follow along. So a representation of G on V is the same as a group homomorphism from G to GLV. Basically, we're taking a mapping of a representation to another representation. It's a little confusing, I know, but you gotta trust it. So naturally, we can show a lot of these like groups, like S3 or D3, which is a triangle, by using matrices. So we give all of these real numbered points on the XY axis, or the Cartesian plane, and we have a matrix that swaps all these points in certain ways corresponding to the actions. So the representation theory part comes in by the mapping of the group action to the matrix. The mapping of the group action to the matrix is what representation theory is. So, what is a sub-representation? Well, a sub-representation is defined as a vector space V is a G invariant subspace. Wait. A sub-representation of V is a G invariant subspace W such that it's like invariant for all elements inside of G. Basically what this means is we can find any mapping of the like the matrices that we've chosen such that all the elements will be invariant. That means that they stay inside the space that they're supposed to stay inside of. This is what a subrepresentation is. But reducibility means that every single point is required and that it basically fills out the entire space. So the space itself cannot be broken down into two different subspaces. So the only sub-representation of V is V and the empty set. Now, that's pretty difficult to understand, but here I've made a bunch of graphs. So here's basically a triangle. I know it's hard to see, but a triangle in R3. We can swap these 2 points at the bottom, and we can swap a bunch of points all at once. And this will create a rotation, or it will create a reflection about a certain point. The problem is in R3, this actually can be broken down into sub-representations. Namely, x equals y equals z, and this line. X equals y equals z has every single action act upon it such that it's invariant. So it takes a point and it leaves a point inside the space. This line, however, is also invariant. You take a point, you do an action, which just happens to be, it changes nothing, and then it also ends up inside this subspace. So these two subspaces are perfect examples of subrepresentations of this larger space. So this larger space is not irreducible because it can be reduced into two different subspaces. Now, is this subspace irreducible? This one has to be because it is only one dimension and it can only be broken down as dimension 1 and dimension 0. So, is this bigger space irreducible? And we can actually look at it inside of the 2D space that it is. We just represent what x and y are, and we take any triangle basically inside this space, and we can swap the points in any way we want. You cannot break this down further into two different one-dimensional things. You can only represent these triangles and S3 as triangles and S3 in R2. So R2, perfectly fair. This is a perfectly fair, irreducible representation. But so is this other one that is of one dimension. So what have we learned? We've learned that representation theory is about mappings of group actions to matrices, such as these. And we've learned that reducibility is about the space it pertains to, not necessarily the matrices themselves, but the space it pertains to. So this space is R3. It is reducible because we can be reduced into an R2 and an R1 space. This one is very trivial because it does nothing, and this one has all of the other things you normally see inside of S3 and D3. So yes, this is representation theory.